So once upon a time, PLCs used to be the kings and the queens of factories. You know, they ruled everything. And back when they were new, people thought they were very smart. You know, they could replace humans and do steps in a certain order. Usually, you know, for old control systems, you bought everything from one vendor, you know, the IO, the control, all the peripherals around it. It was just all from the same company, a very homogeneous environment, you know. It all kind of played nicely together because you bought it together. Now PLCs have been on the market for like 40 years. You know, there's no hydraulic PID loops anymore. They're all electronically. And PLCs, in the grand scheme of things, they're not that smart anymore. Yet they're still everywhere, in fact. And you know, with the evolution of the PLC market, many vendors have also come along, and modern factories are also not usually built as one. It's more like you build as you go, so you end up with lots of different control hardware from different vendors in there. You know, being limited to just one vendor would be quite limiting nowadays. So, you know, in a modern factory, a PLC is just one piece of the big puzzle. There's a lot of other smart software behind the whole factory that like decides what parts to get from the storage in an automated way. Or, you know, you can have AI that checks whether a weld was good just on the current curves of the welder. There's a lot of things you can do nowadays. So the overall software environment in a factory has gotten way more heterogeneous. There's all sorts of different stuff now working together. And for all these things that you have in a factory, you know, you have lots of different software. You want the best in class of each. You want the best machine control. You want the best image recognition. You want the best predictive maintenance AI. You want the best databases, the best historians, and so on. CODESYS, you know, we're good at that first one. We're good at machine control. CODESYS is the best in class in hardware independent PLC engines. But is CODESYS good at image recognition? Do we even have any products there? Not really. So now the question is, you know, how can I use all this best in class software for the different things I want to do in my factory all at the same time and have them work together, not just coexist and never talk to each other. So this is where the CODESYS Control SL extension package comes in. So the goal of this package is to allow you to connect CODESYS' Linux-based SL products. So the Linux SL, the PLC Next SL, the Linux ARM SL, and so on, to other software on that same Linux device. So one acronym that was used in the sentence is SL. Many people don't know what this means. It's very simple. It stands for single license, and it means that instead of CODESYS or us at CODESYS selling licenses in bulk to PLC manufacturer like Opto22 that we'll hear from later, you as an end user, you know, you just buy your off-the-shelf IPC, put Linux on it, and then buy a single license of CODESYS from our online store. So all our SL runtimes are available at us.store.codesys.com. And this API is primarily intended for those SL runtimes that you just buy one-offs or multiple. So what's the main use case of this extension package? One of them is to have existing C code, maybe from a legacy application, and be able to keep using them with your new CODESYS application. Another one is to, just have a function block or a function in CODESYS that then goes and runs some external code that's outside of CODESYS. We also support adding local or remote I/O that's on the block that might be on your IPC or industrial, might have I/O on your IPC and you want to use that within the CODESYS runtime. RSL runtimes are hardware agnostic, so they don't know anything about what's on your hardware. But with this extension package, you could integrate that I/O that's specific to the hardware you chose into the CODESYS runtime and have it show up like you would any other I/O that's used with CODESYS. There is some new features regarding retain memory, and that is for var retain and var retain persistence you have in your application. So that's variables that can keep their value throughout power cycles. There's some cool new stuff you can do there. We added the ability that if your hardware has like a stop switch to like start or stop PLC execution, you can now integrate that with our SL runtimes. Again, something where you can take our standard product that's hardware agnostic and customize it for the hardware you chose. You can also have stuff that happens in some other Linux application. Just trigger the execution of a 61131 task. And you can also register some event handlers for certain events in the application that happen. Like anytime you download an application, you could do something. And you can, the runtime has a PLC shell. You can now also access that from Linux. Yeah. Now, before we go any further into the extension package, I'd like to take a little step back and talk about some of the basics of Linux. And in particular, I'd like to talk about processes. On Linux, every application or every program you run spawns as a process. And then within that process, you will have the code of that program. So it's the CPU instructions that tell it what to do. Usually on Windows, that would be a .exe file. On Windows, that's stored in a .bin file. But then when you run the application, it also needs memory. And that memory that the code writes all its values in is also associated with the process. So these processes, they're like very close down units. If you run this, you can run the same application twice. It'll spawn two processes if you run it twice. Like two instances of Word, for example, would run in two different processes. And each of them has the code in it and the memory. And the restrictions of process are that process 1, for example, cannot access process 2's memory and vice versa. So process is really encapsulating the application from the rest of the operating system and other processes. So when you look at extending an application that runs in a process, like the CODESYS runtime, this then leaves you two options to extend that program. The first one is you can somehow add more code to that process. Then the code runs in the process and can access the full memory. The other option is to just have two different processes and figure out a way how they can talk to each other and exchange data. That's then called interprocess communication. So here's a little picture of the first use case where you add code to an existing process. So this is on Linux. This is usually done using shared object files, kind of a piece of code that is loaded into an application after it's started up or while it starts up. And this code, it's running in the process. So it gets full access to all the memory and all the user data. So it's very easy to use that data. On the flip side, though, that code has full access to the memory of the existing process. So it makes it very easy for that code to abuse the data that is in the process. But it's just from a security perspective, it is dangerous to be able to freely access data, whereas from an engineering perspective, it's awesome to freely access data. So these are like two flip sides of the same coin that you need to weigh against each other. Another restriction of loading code into an existing process like this is that the new code must be compatible with the existing code. And since the CODESYS runtime is written in C, that means that your additional code must also be C code. You couldn't add like Java or Python into it that way. Now, the next option would be connecting two different processes together. This allows the two different processes to exchange data, and this is done through interprocess communication mechanisms, short IPC. So this can be a little confusing for industrial people because we already know IPC as the industrial PC. In this context, we're using it as interprocess communication. Common ways to do this are share memories or just a simple UDP or TCP connection. On Linux, you can also just make file descriptors. So it's kind of a fake file that that belongs to one process, and any data that another process writes to that file doesn't actually get written to this file system. Instead, it just pops up in a memory buffer in another process. So that's a very common way to do things. And one that's Linux specific and very high performant is actually Unix domain sockets. They work a lot like regular sockets, but only between two processes. So the pros of having separate processes is that the memory in a process is protected against accesses from other code. So the blue code cannot easily access the red memory, and vice versa. And you can use completely different languages in the two processes. So process one is a CODESYS runtime in C, and then process two, which might be in AI, could be in Python, Go, Java, any language that you choose, really. That's the pros, but on the con side, again, we have kind of the disadvantage of memory access being protected. That is that, you now actively need to exchange data. You can't just get the information from memory that you would like. So this is really a trade-off where security and usability like butt heads with each other, and there's some serious trade-offs to be made. Yeah. So now, if you use the extension API to add code inside the existing CODESYS runtime process, you can create your own runtime component using a shared object. It uses CODESYS specific mechanism to then have what we call externally implemented functions. That basically means you have an IEC function that then executes some C code in that shared object. To create them, the extension package contains a sub-element called the extension SDK. And that's really some make files, some header files, just stuff you need to compile C code, really. Just quick note that this new extension SDK is unrelated to the existing C code integration features you might find on our website. The C code application integration is more you add C code in the CODESYS IDE and then it gets downloaded with the application. Whereas this extension SDK is really you compile your shared object on the side and then load it into the runtime yourself, and the CODESYS IDE never really knows about it. So some caveats to this is that you cannot easily access IEC application variables. You can't debug it that easily because if you step in, CODESYS will just step over it. There's no setting a breakpoint and digging down into the C code. As I mentioned, also it's only C code, or any other language you can wrap in C. That's additional effort. And it can have direct impact on the existing runtime process. So you can introduce security and performance issues if you just add a shared object to the CODESYS runtime. So from a security perspective, might be not great for your application. Now, going to the other solution with running CODESYS in its own process and your external code in a separate process, we have an API where you can create a function in your external code, but then have it called from the CODESYS 6.11.31 code. And we use Interprocess Communication for that, and we chose to use Unix domain sockets. So Unix domain sockets are a standard Linux thing, and they are implemented in various technologies, Python, C, Java. All these languages can use Unix domain sockets. And just, you have a function, and you can call that. And we did some performance tests, and just one function call round trip through Unix domain sockets twice only takes 50 microseconds. So just for scale, that means you can do this 20,000 times per second. Usually you don't call functions quite that often. So performance-wise, this is really nice, and it's actually faster than using simpler stuff like a shared memory. Yeah, and we also have a similar mechanism. The Unix domain sockets are also used to add I/O that's on your device into the CODESYS runtime. We have some generic mechanisms there that we can just configure. Now, so a little background on Unix domain sockets. So what is it? It's a local interprocess communication standard. It's really standardized. Works like regular sockets. You send messages, and then on the receiving side, you have a read or a select function that then either reads directly what's already there or waits for a message to arrive and then reads it. So if you use regular sockets, then this is going to be familiar. They have instead of using an IP address and port, they use a fake file in the file system as their identification. So when you open one of these Unix domain sockets, you kind of give it a path, a file path to open. And from a security perspective, one great advantage of these is that you can only access them on your local machine. So they don't go over the network. So the two processes actually need to run on the same machine. So a hacker couldn't just kill off your one process and connect it to his that's running on some other server somewhere. Now, you might wonder, is this like a special feature of Linux or not? Unix domain sockets are standard in POSIX systems like Linux, and they're directly implemented by the kernel. So it's not a distribution feature. It's actually the Linux kernel itself that provides them. And they're fast because they don't involve network stacks. So if you would do a TCP connection between two processes, that would, it uses the loopback network adapter. So that stays in the box, but then it still runs through the full TCP stack after sending and between send and receive. So that would be a lot of overhead. Unix domain sockets don't have that. That is very nice. And the way they're implemented, they also avoid context switching. And context switching is kind of when the CPU alternates between doing different tasks. So it's a fundamental thing of multitasking. And it's just like when you multitask and switch between two tasks, there's overhead, and going back and forth between doing two things probably gets both done, but it takes longer than if you just did one, finished it, and then did the other. So on a CPU, it's very similar. You want to avoid context switching, and Unix domain sockets definitely limit how often the CPU switches context, leading to less overhead and higher performance. Like we said, leading to this sub 50 microsecond round trip time. Now a couple of details on how you can do some more stuff. So triggering external event tasks. So CODESYS provides a Unix domain socket that is like standardized. And every time you send a message to that standardized socket, you can run an IEC task. So you just, in the IDE, you can set up your task and then say it's an external type task and what event to run it on. And that is very nice, because if you have code in your PLC application that should run when, like a database update arrives or something, you can easily execute that 1131 code to run like this. And if you want to test it on the command line, it's a simple one-line command. Do that. Yeah. And on a similar note, you can also register event callbacks for when things in the IEC application happen. Like every time the application starts or stops, or there is an application, or when it's reset, or when a new application is downloaded. You can do all that, which might be great for like a monitoring application or something. Another feature is you can add a run stop switch. So many PLCs have this big switch you can flick from stop to start, which kind of controls whether PLC logic is allowed to run or not. If you use our off-the-shelf SL runtime, obviously it doesn't know that your hardware has such a switch, but we have the ability to connect that, and it uses these fake text files, or one fake text file. So whenever you want to run, you just write run to that file. If whenever you want it to not run, you tell it to stop. Again, this is very easy to do from the command line, and also very easy for external applications. You just open that text file, write run to it, maybe flush it, and the CODESYS runtime will run, or it'll block execution if you send stop. A little caveat there is that if the hardware that you have so if it's one of our more hardware specific SL runtimes like the PLC Next or the WAGO PSC, those already have a physical switch, so we don't provide the text file there because we already implemented that switch. Lastly, one topic that I think is often overlooked is how retain variables work on our Linux SL runtimes. So for background, retain variables are those that are supposed to keep their value across two power cycles. So the way we do that is, by default, we have a file with all the retain variables that gets written when the runtime shuts down. That works great if you tell the computer to shut down. But if you just pull the plug, the computer doesn't shut down, the runtime doesn't shut down, it just dies. So no retain variables are written, which means retains are lost on power fail in that case. Which, by the way, on modern Linux machines, it'll go fine to just pull the plug like 50 or 100 times, but at some point you'll likely kill your file system like you do in Raspberry Pis when you just pull the plug. So be careful there and take that into account. Now, how can that be improved with our SL runtimes? So some hardware has memory-backed RAM that could be used to store these retain variables. And since it's memory-backed, it keeps its value even though you pull the plug. And you can connect that to our SL runtimes through a shared memory. So you would have an application that opens that memory-backed RAM and then maps it into a shared memory, and then the CODESYS runtime is just told to allocate all the retained variables in that shared memory. So that's a really great feature that I recommend everybody to take a look at if you want to use retained variables in your applications with a Linux SL runtime. Yeah, here's the settings if you want to go back to. All right, that was quite the nice slideshow, I would say. But in my experience, I like to just see stuff in action. So my colleague Adam has prepared a little demo here using an Nvidia Jetson Nano, which is a hardware that Nvidia is really pushing for AI applications because it has a very powerful GPU for its size. And yeah, we're running a CODESYS runtime on there that is connected using that interprocess communication method to a Python script running OpenCV and doing some image recognition. And with that, it's over to you, Adam.
Yeah, thanks, Lars. So I put together a demo with the extension API, and I guess I kind of want to just, for one, show you the demo, then talk a little bit about kind of what I went through to learn how to use it. I mean, I went into this knowing nothing about it, and still 2 months into CODESYS, so it was a learning experience, and yeah, I just want to kind of share how I got something up and running. So like Lars said, we have a Jetson Nano here that is kind of a platform that is designed for AI. It has a built-in GPU, and we decided a cool application might be to do some image recognition, and then pipe that using the Unix domain sockets into the Linux runtime. So I'll show you that, and then as well I want to go through the distribution a little bit. So we actually when you get this product, what do you see, and what do you get? And then I can as well, I saw there was a question about documentation, so I can just show you kind of what we got for that as well. So just get this one. So we created just a Python script that I started off with the example that comes with the distribution. I went to GitHub and found an image recognition app, and just kind of married those two up, so that the example app in the distribution just did a counter. Basically, there was a Python script that had myvar equals myvar plus 1 essentially, and then I just converted that so that it's looking at these detected images, and then here you can see in CODESYS we're detecting the images. Hopefully you guys can see that. I know sorry. One second. There we go. Okay. Yeah. So this is, like I said, this is just a simple project I found on GitHub, and as you can see, it's detecting images, it's detecting myself, it's detecting the chair behind me. with a certain probability that it is that object. So, you know, if I get out the camera, you know, it's, you know, 90% probability or higher that that's a chair, and well, you know, that's correct. Person, a few others. Suitcase, that's not right, but let's see. Handbag. Yeah, that is not perfect. That, see, potted plant. So, yeah, object detection. Okay. So the, you know, the code, I guess, behind this is very simple. I can show you some of it. You know, I think let's start. So we have a function block. The function block name matches up with, so this is what's running on that Linux machine. So this is the code. It just, I put it, you know, local because you can probably see it a lot easier. So the function name, and this is also what you get when you with the example project in the distribution. So this class is what's being called, and then here I am, you know, I have a queue that's coming from a different thread that's doing the image detection, and that I'm, you know, essentially casting it into a string that then is, you know, being set to that function block. You know, so this is the confidence, this is the probability. So these can then be seen on the function block right here. So this is, you know, parameter out1, parameter out2. So this is kind of how the IC variable is pointing to the Python script. Okay. Very easy to set up. Yeah. It was, yeah. I mean, it probably took about an hour to get this running. Okay. So let's see here. When you install the extension API, so a directory will be installed on your user, in your user directory, CODESYS control SL extension package. And within there, so this is where, you know, you have these examples. So, you know, we have a C integration example where it gives you a library that you create the header file in this C file that you can then use to compile the shared object that you would then install on the Linux machine. So events, this is where you can, you know, they have a Python script for you that you just run on the Linux machine, and then they also have a CODESYS project. So they have, you know, good examples for each one of the features of the extension API. So the one I guess I started off with, I did this external call. So if you look at this, you see a lot of the same code. So this is basically where I changed the project so that, or I'm sorry, changed the default script so that it took in the data that was coming from the object detection. Okay. And then as well, it gives you the CODESYS IC project as well. External event. So you have a shell file, and then project. So it covers all the capabilities. I think it does a pretty good job of giving you something to start with, and then you can kind of take it and run with it, like I did with the object detection. And then just the same. So documentation. Basically, so there's going to be a CHM, and in here it goes through the steps for specifically getting those example projects up and running. So one, let's see, the extension SDK. But yeah, that was another thing. Within the distribution, there's the SDK. So this is what you'll use to compile the .c and the C files that are generated from your CODESYS library into shared objects. And that process is described in this section. And this is I went through this, and it was simple. It took maybe an hour to get all this up and running. I have not a lot of experience with C, and I was able to follow it pretty well. So yeah, linking your own IO, basically everything that that Lars just went through. We have pretty good documentation for, and some good example projects. And that's about it for me. I think it's it's a really cool product. The possibilities are endless, and just the ability to take this device, this Jetson Nano, that I think is a really cool device because of its capabilities for doing AI, installing the CODESYS runtime on it, and then that in itself is cool. But then from there also being able to take the next step and kind of opening up all the interprocess communication on the Linux device, I think is very powerful, and that we should see a lot of cool applications from it. So so that's my time. I think there's going to be questions at the end, Chris. Is that right? Or
Q&A will be after this. So if you want, you can, if you think you might forget your question, there's a little chat box where you can put the questions in for the Q&A right now even, and then we will read them out. And before we give this all back, I have one more slide. That's a quick summary of how to get this SDK. So the best way is to use the CODESYS installer tool. So you just type in CODESYS installer in your Windows search if you already have the CODESYS ID installed. And then you can change your existing installation to include one of our Linux runtimes. And if you do that, the extension package will be installed by default. And then you will find all the files that Adam showed you in this directory. And I just realized I also forgot a very important part on my slides. What does this whole thing cost? And the great news is that it is included for free with our SL runtimes. So you don't need to pay anything to use this new feature.